remember, when we talk about technology, day-old technology is old technology. We have to have new one. So here, this is the problem. It's something that you probably had it in those of you mechanical engineer, fluid mechanics course, that you pump water from a lower height to a higher height. And then to do that, you need to have a pump, right? To pump it. And then on the reverse, this pump would be turbine. So you get power out. And then the energy storage efficiency would be the ratio of the and turbine power you get out divided by the pump power you have to use it. So this is homework number 2. I thought maybe you guys would be able to do it by Friday, Thursday, but we'll see how far we get on the lecture on pumped hydro energy. Is it okay? He still doesn't believe you. He's looking, checking it out. It's there. All right. The next 2 days we have some conflict at 2 o'clock, right? You guys aware of that conflict? Tuesday and Wednesday? You don't know what's going on in the world? Something's happening in Russia? World Cup. So the semi-final games are 2 o'clock tomorrow and Wednesday. So I'd like to see at least the second half. So you probably take a break after an hour or 45 minutes. We catch up, don't worry. All right. So, energy storage system. Remember that sheet that I had? Energy storage system and the 5 different categories, and within each category were different types of category. The first one was mechanical energy storage technology, the first category, right? Then pump hydro energy storage was the first one in that category. So we're going to talk about that today. Okay, now you guys can check me out. I think at this moment, at this time, 95% of energy stored is hydro. Okay. Because these are next to power plant. Remember she's gone. The whole idea, oops, we still here. The whole idea is if you have let's say a power need, it's a power and this is a time. If this is your power need, okay, so if I operate this point and store this energy and use it at that time, then I don't need to produce this much power, right? Because if you don't have power storage, you have to produce this much power. And electrical companies, they cannot do that. I mean, there's lots of waste of time. Then what are you going to do with extra energy? Destroy it in the electric bank. You know, that's one way. Have lots of resistors, put the energy there. The resistors, the temperature will increase, then it would be transferred to the air. That's waste. So the idea is instead of doing that, operate less and store this energy and use it when it's needed. So most of the stored energy next to power plants are the hydro. People think batteries. Batteries not there yet, okay? Maybe in future, 10 years, 20 years, this battery storage will increase. There is no doubt about it. But the hydro is not going to decrease because you already have this plant. You have this the pumped energy storage and then use it that way because even if you have battery, this might cost much less than the battery. So you can say, oh, I'm going to build huge batteries next to power plants. But this system costs a lot less than having the battery. So this is what we're going to do. So pumping water uphill using peak off electricity stored energy, the one that I mentioned. Letting the water move downhill and driving the generator to produce electricity for power when needed. So it's kind of hydropower. But hydropower usually, they have the reservoir at top of the mountain that in which the rain comes in or rivers come in, that's how you have the water. In this case, you pump the water from underneath the beginning bottom of the hill, you pump it up. But after that, it's hydro. You just open the gate, and the water goes through hydraulic turbine, and you get the energy out. So here's the bottom line, exactly what we have. You have a lower reservoir, you pump it, the upper reservoir, and the discharge, this is charge. Discharge you have turbine. This is very simplistic design. And then you have efficiency. In this case, efficiency and exegetic efficiency are the same, because both of them, this type of energy that you use is electricity. Electric energy, all of it at exergy. Okay? So it would be the power, and it could be 70–80% nowadays. And this is said 95% of energy stored in the world is the hydropower. Slow me down when you think I'm going too fast. Make sense, Kevin? You tell me something. You don't have to say something. Just use your hand this way, slow down, all of that. Okay, this is one kind. Looks good. Pump hydro energy storage, again, you pump it up, and then when you need the power, you just open the gate and hydraulic. By the way, we have Dr. Bakhtari there in the back. I'm trying to recruit him to teach a hydropower course for the spring semester. So those of you guys interested in hydropower, don't graduate till the spring semester and take the course. So here's what we discussed at the diagram that I have. Instead, shaving, that's where you need more. That's how the whole thing is. This idea is you save the energy when you don't need it, and then use the energy back. So basically, you shave the peak. And when you shave the peak, you basically operation would be much better because you don't have to generate electricity. Why pump hydropower storage? Least response time as compared to other electricity generation sources, except the battery, of course. Could you start within less than 10 minutes to feed electricity load? So right away, if you open the gate, hopefully I'm right, here Dr. Bakhtari knows more than I do. In 10 minutes, you get your electricity. So here's some of the types of project. Classic hydropower plant, that's when you have a dam, right? That's what it is. 3 to 5 minutes response time. Pump storage hydropower is the same thing. When you want discharging, it's the same phenomenon. Just open the gate, so it's 3 to 5. If you have a secondary, let's say, furnace and a turbine, if you want to burn natural gas, it takes 1 to 3 hours to get electricity. So basically what's called topping cycle. Oil, the same thing, coal further. Nuclear plant, start up, maybe at least 5 days. It will probably take more time. So that's why this is quick response. When you need the power right away, you can use it. And that's what most of the hydro storage are. Merits of pump hydro energy storage. It's already established technology. It's nothing new. Maturity and extensive operational experience. Lots of experience are there. Reasonable round trip efficiency, large volume storage and long storage period are possible, right? Because what if you need for many hours instead of not half an hour. So because it's a large capacity, you can store lots of energy out there. Good start to stop flexibility. Long life, 100 years, low cost of storage. Okay, when you build it, initial cost may be high, but it's still not that high. But when you build it, it's there, unless you do something to it. And there was one place in California a couple of years ago, had a problem with it, but it's safe. History of pumped hydro energy storage. Look at that, 120 years ago, Italy and Switzerland had it. 1929, Rocky River pumped hydro energy storage. Right now, there are so many of them. Look at that. Let's see what we got. Can you see it from the back? So here is comparison. Pumped hydro energy, gigawatt. Go all the way 160. Look at the other ones. Thermal, electrochemical, electromechanical, nothing. These are the stable. Do you see that? Kevin, you have good eyes, right? And right now what we have, grand total, this is 2017, 133 gigawatt of power. And for example, this is electromechanical, look at the number, point something. Electrochemical, thermal storage, look at pump hydro. Large power plants, okay? And what is the US? China is number 1, Japan is number 2, United States number 3, and then of course the other countries that are following too. So that's what I said, if you compare to that, it's over 95% is pump hydro. Okay. But that's good, whatever has been going on, right? There are other, now you guys think about electricity, batteries, okay? Sure, the battery work should continue, but there are some additional ones that there are lots of, remember our list was 19? There are other ones that right now they're built. Some of them are in the research period, trying to improve the efficiency, because one of the things, what's the cost? And then efficiency, right? And storage efficiency, these are the two important. So as you can see, there are a huge number of 128 out of 133. So it's more than 95%. It's 5 over 130. Okay, 4% is the other ones. And hydro is 95, 96%. Issues, whether we have issues. Okay, you have the geography has to be correct. That means if power plant is in a flat area, you're in trouble, right? Because you like to have the power plant be next to a hill, and the top of the hill should be some reservoir, some opening that you can store your water. So that's always an issue. Large land use is needed. Again, you want to make a man-made lake at the top of the mountain. Okay, so it takes a lot of space, and also down here at the bottom too, because when you discharge it, and you need another reservoir at the bottom of the hill. So you need 2 large area that you can store water, sometimes here, and those are the issues. Low energy density, okay, per unit area, the energy storage is a small number. High initial investment costs, long construction period, and long time to recover investment. These are the issue right now, and the cost is high. Environmental concerns, right? Remember, you have these environmentalists on your back, whatever you do. Right now, they don't like hydropower because it changes natural life. Remember, anything you do changes natural life, you're polluting the environment, okay? So if you think that way, whatever you do, you have to be worried about, am I changing natural life, okay? And usually the answer is yes. It would be very hard not to alter the environment, don't do anything. Okay, now here's a comparison between batteries and pump hydro. Battery costs 3 times as pump hydro energy storage. Cost of pump energy, hydro energy storage was 1.5 million to 2.5 million per megawatt installed in 2017 as compared to battery 2.5 to 7.5. In terms of units, the cost is per megawatt hour. Remember, that's energy. When we talk about megawatt, that's power. The question is how much energy you get in, because as soon as the power, okay, can this operate forever? You need huge reservoirs. So there is a limit how many hours you can operate from that. So these are the costs. So now you can see for power plant, it doesn't make sense to store energy in batteries to build it next to power plant because it costs a lot of money. Now, here's another design. Remember the normal one you have to have a reservoir at the bottom of the hill and reservoir at the top of the hill. Why don't you use some volume under in the ground? So there might be lots of cavity holes, all of that. So basically, you can pump the water. It goes. This is let's see. You pump the water this way, storage. Piston goes up, and then high pressure. The piston goes down. The water goes up to the turbine generator, and you run it. So this, in case there are cave under the ground. So you remember, you need two reservoirs at two different heights. So this normally one is the land level and the hill level. This one is land level and the cavity inside the land. So there are lots of different people are working on different designs. Remember, we have to do a project, right? And what I do, we go over different type of storage, and what you do, you pick up one of the title and you go much beyond that what I'm discussing. That would be your project, okay? And hopefully there are 19 different types of project, and there are, I think, 14, 15 of you. So suddenly not 10 people say, we're gonna do this. Hopefully we have 1-to-1 match, and it would be much easier to do that. Okay, so if you do energy analysis, so basically you have a reservoir, you pump it up to high reservoir. This is the energy balance neglecting nuclear reaction, right? You guys have seen this in the Kowalski's course or undergraduate term, okay? If you have a system, rate of change of energy, this should be lowercase t. You just made a mistake on that. Can I fix it, you think? Oops, where's that? Okay, rate of change of energy in respect to time. This is a given system, not the whole picture. Okay? Because if you just look at this or that, there's no change of kinetic and potential energy. This is rate of, what do you call this, Q dot? What?
So,
Rate of what? What do you call it in an undergraduate course? Rate of heat transfer? Kevin says that's wrong. What are you transferring? Energy. So it's energy transfer, rate of energy transfer via heat interaction. Okay? Remember, as soon as I say something transferred, that means it went from here to there, right? Heat is not a problem. You're transferring energy. Okay? And this is, what is this? W dot. Rate of work done by the system or the system. You don't say work transfer. Why do you want the other one to say heat transfer? Okay. This is energy transfer via work interaction. This is energy transfer via heat interaction. Okay. And then we have some of the energy coming into the system. Remember, enthalpy is U plus PV, or P over rho. And if you say everything is room temperature, environmental temperature, dealing with liquid, which is on the internal energy is only function of temperature, they would be constant. Okay? So then it would be simplified to, now here what I did. I wrote it completely different. So this is the energy of the fluid at some point. Then if you send this fluid to a pump, its energy increases. It has to go through some tubing. There would be energy loss due to friction. So it would be energy of the fluid at higher state. So this is the energy balance, everything in the unit of height. Okay. Now that's the charging or pumping process. If you have discharging or energy generation process, again, now this was the fluid that's at upper level, mine again is a friction loss, so there is the energy transfer, minus the work you get from the turbine would be energy of the fluid at state 1. So here, when you pump it up, there is some losses due to friction, and you have to provide energy in the pump to run the pump. When it's discharging, again there would be some losses through friction, and then you get work from the turbine. Now, then I'll put down the kinetic energy. That's a kinetic energy term, right? It was 1/2 mv squared, you divide by gamma, is a v squared over 2g. To be correct, kinetic energy term should be kinetic energy alpha times v squared over 2g. So what's the alpha? Alpha is a function of Reynolds number. You know what Reynolds number is? Is there anybody who doesn't know what Reynolds number is? Reynolds number. Reynolds number is that number right there. RE is Reynolds number. Okay? Who was Reynolds? Do you guys remember who Reynolds was? Osborne Reynolds? You don't know it? It's an Irish guy, right? 19th century. He's the father of fluid mechanics. Okay? Now, this Reynolds number basically is speed of the fluid times density of fluid times some characteristic length divided by viscosity. Remember, viscosity is a property that works against the flow. The higher viscosity, the fluid usually is slower. The smaller viscosity, it's easier to push the fluid higher. Okay? For example, gases have very small value of viscosity. On the other hand, liquids have higher viscosity. Now, you have the stuff number. This guy, you calculate Reynolds number, it's a flow through a tube or flow over a wing of the airplane. Those are all flow, right? And then based on that, you find out it's laminar flow or turbulent flow. You know what the difference is? Laminar flow basically flow is laminated. If you have a faucet, if you open it a little bit, you can see water comes in easily enough. If you do it all the way, there is some mixing. The best example of turbulent flow is, does anybody smoke here? No, just cigarette, right? You're not talking about anything else. If you have cigarette and you put it here, the smoke, right? The smoke goes up. If I hold the cigarette while it's lit, is there any way for anybody to predict what's going to happen to the smoke? There is no way, right? It's a turbulent flow, even though its speed is low. But since this number is 10 to the minus 6, the Reynolds number is high, it's turbulent flow. Turbulent flow is on a steady flow. Laminar flow is usually steady. It doesn't change as a function of time. But turbulent flow is unsteady, so everything changes as a function of time. And I see if the best example, just have a cigarette and see how this smoke moves out. So if you want to find out about this friction, how much energy you lose in the friction from storage 1 to storage 2, we have to learn about fluid flow. Okay? So now remember, the idea is that kinetic energy term said it has to have a coefficient there. And the coefficient alpha is a function of Reynolds number. And this is another question is, okay, if I calculate my Reynolds number in that tube, what is alpha? All right. First of all, viscosity, a property which shows resistance of the fluid to flow. Then you have Newtonian fluid. So if I have a stationary plate here and some fluid, and then I move the upper plate with some speed u. Okay. If you have Newtonian fluid, it usually is linear. This is velocity profile, lowercase u. Okay. So velocity is 0 at this point because it's attached to this plate, the molecule. The molecules that attach to that plate has a velocity of u. The shear force works in this direction. It's against the flow. Okay. And if you have Newtonian fluid, when was Newton guy around? Do you remember him? Were you born? When he was around? No? Do you have any idea when? Remember, I'm old, you have to talk louder. About 1700? Just about 1700. So you're talking about 300 years old history of this stuff, okay? So sometimes it doesn't feel good. You're still trying to learn what happened 300 years ago. Okay. So here is Newtonian. Most of the fluids are Newtonian fluid, except one of the most important fluid. What's the most important fluid in your body?
Water.
Water. Okay. What's second most important? Blood. Blood is not Newtonian fluid. So that relation is not true for blood. Okay. And it's lots of people try to simulate what goes on in the heart and how the blood goes around, goes to different parts of your body. You cannot use that relation for. Okay, here is some in numbers for some of the substance. You have fluid, viscosity. Okay. Density. Look at how mercury, how dense it is. And we have this is kinematic viscosity, meter square per second. Okay. Is the picture good? Remember, there are lots of people going to watch it tonight. If the picture is not good, if they call me, I send them to you. They say, okay, it was her that took the pictures. All right, now Reynolds laminar flow, if you have flow in a pipe, if Reynolds number is less than 2300, Reynolds number would be based on diameter. Okay, that characteristic D is diameter for the pipe. If it's over a wing of the plane, is the length of the wing. Okay, so that's, and velocity profile, look at this, is a parabola, right? And you figure it out, that is, if you want to calculate this alpha, how do you calculate this alpha? If you say kinetic energy is 1/2 mv squared, so if we said, okay, alpha over 2 mv squared, and now it would be integral 1/2 m, right? U, v is u squared dr, right? You integrate between 0 and r. When you do that integration, it turns out alpha is 2. So when you go use your energy equation, in front of kinetic energy term, you have to put a 2. Most of the time, you don't see that. The reason is life is full of the turbulent flow. There are very few laminar flow in real life. Then you say, why are we studying laminar flow? Well, if you have viscous flow, it's all laminar. Lots of viscous flow is laminar. But again, remember, when you guys started to run, you learned to walk first, right? As always, as you walk first, then you start to run. Same situation here. You learn to deal with laminar flow, then you will deal with the turbulent flow. Now, turbulent flow is different. The velocity profile is different, okay? And by the way, U0 is the maximum speed. Here, the same thing, the same. Now, it depends on M, then your alpha would be different. M could be different. As M gets smaller and smaller, look at the alpha. Gets smaller. So since real flows are mainly turbulent, lots of people, they don't use alpha because this is such a small number, 1.3% and all that stuff. Remember, we're trying to find the properties, volume, pressure, height, maybe speed, pressure, and height. You need to find the friction. Then we can calculate how much power we need to run the pump. And the discharging case, when we calculate friction, how much energy we get back due to from the turbine, right? That's all. Let's do an example. I'm going to try to hydroelectric power plants taking 30 cubic meters, so that's volumetric flow rate, right? Q. Many times in fluid mechanics, you use Q for volumetric flow rate of water through its turbine, and discharge it to atmosphere at V2 equal 2 meters per second. The friction loss is HF 2 meters. Assuming turbine flow alpha is 1.06, estimate the power in megawatt extracted by turbine. Okay. Simple stuff. That's your energy equation, right? what we have is state 1. Whenever you see this, that means it's atmospheric pressure right there. It would be here to atmospheric pressure here. The energy at the top is energy at the bottom plus the turbine work you get and friction factor. Okay? There is gamma, which is a specific weight. You know, rho is density, is kilogram per cubic meter. If you multiply by G 9.0806 or 7, you get unit of weight per unit volume. So it would be specific weight. That's what gamma is. And up here and in here, pressure is the same, atmospheric. This is usually a large reservoir. When you drain something, there is not much, very small. The speed of the liquid water is decreasing, so you can assume that's 0. So if you apply those assumption to this equation, so on this one you have Z1, kinetic energy state 2, turbine, and friction. So what's the turbine? You solve for it, 100 meters minus, that was 1.06 times 2 squared divided by 2.981 minus 2, so that's 97.8 meter height. So the power, P, is mass flow rate through the work of the turbine, right? That we know. Mass flow rate is density times volumetric flow rate, okay? And then the power per unit, so you have the G by T, HT. So now if you look at all this, remember units have to cancel out. I didn't write it. You have to go kilojoule and all that stuff. Do you want me to do it? Unit conversion. You guys are okay with this unit conversion? How the hell we got megawatt? So what do we have? We have kilogram meter square per centimeter cube. The second cube? No. The meter square. Are we okay with this? Let me write it down on one side so I don't forget. So I have kilogram meter square second cube. Is that what you have? Can you become megawatt or am I made a mistake? Maybe I turn this off. There's too much stuff there. Let's see. Kilogram meter square second cube. A kilonewton is a kilogram meter per second square, right? The kilojoule, the kilonewton meter. A kilowatt is kilojoule per second. A megawatt is 1,000 kilowatt, right? Did we have a megawatt? So let's see, kilograms we cancel out. Meter square we cancel out. Newton we cancel out. Second cube cancels out. Kilojoule we cancel out. Kilowatt we cancel out. So we have megawatt. So the unit conversion is correct. You don't have to multiply by anything. You just need to know. Remember, these are dimensionless one, right? Here I have kilojoule is a kilonewton meter. That's by definition. So kilojoule divided by kilonewton meter is dimensionless one. You can always multiply by dimensionless one or divide by dimensionless one. I always write my units this way because it's very, very hard to say, hey, what's the outcome here? Okay? You're okay on that? Kevin, you're okay? I wasn't too fast? Lower it. So anyway, the idea is now using that equation, but still, in this example, friction was given to you. When you try to analyze this in your life, nobody's going to give you the friction. You've got to figure it out. What is the frictional loss? So the question is, can we do that? Let's do another example. Pump delivers water. So that's gamma of water, specific weight, 62.4 pound force per cubic feet at 1.5 cubic feet per second. The machine at section 2, which is 20 feet higher than the reservoir surface. The losses between 1 and 2 are given by, okay, now here is a recorded relation for frictional loss, where K is given 7.5 as dimensionless loss coefficient. Take alpha of 1.07, find the horsepower required for pump if it is 80% efficient. Okay. So we have initial condition. If that's 0, this is 100, this is 20. The pipe diameter is given, pressure is given. So you use the equation, right? State 1 plus the power that you add in the pump would be energy at the exit plus whatever you use. A part of that energy is lost. And HF is K V2 squared over 2G. Okay, and in state 1, remember this large reservoir, the area is high. So if you take a little bit, water goes down, you can assume the velocity is 0. Z1 is 0. So the pump energy required would be delta P, Z2 plus these two terms. This term is kV squared, so it would be alpha 2 plus K if you factor out kg squared. Velocity is volumetric flow rate over A2, the area. Area is pi over 4d squared. Right, these absolute numbers. Velocity of 30.6 feet per second. Those of you taking fluid mechanics course in undergraduate, these are nothing for you guys. Do we have somebody who has not taken any of this course? You haven't taken, have you, have not? You have not. Okay, anybody else? Everybody is expert? That's great. So you calculate pump power, right? It's absolute numbers in. You get the head, 133 feet. So now you have to convert it to power, which is mass flow rate times work per unit mass. Okay. So here's all the numbers. You can do unit conversion. You can find foot-pound force. You can convert foot-pound force to horsepower. 222.6 horsepower. So I'm trying to slowly, these are all part of the whole process. Remember, the whole process is going from state 1 to state 2. And now to get example with the turbine, example with the pump. And so far, the friction factor either was given or we had simple relation, K times kinetic energy. Right? So then, in the actual pump, this is how much is needed. If pump is 80% efficiency, then you need more power to run the pump, right? If you input in that much electricity, you get that much from the pump because of 80% efficiency. All right, let's see what else we got. Oh, example 3. System example 1 is used as pump hydro energy storage, turbine efficiency 85%, and pump efficiency 80%. Determine overall storage efficiency defined as actual turbine work output divided by actually work input. Right? That's how we define the storage efficiency. The power we get out divided by the power we get in. So this is discharging part. The charging is the reverse. So for example 1, in the power generation, we already have determined the turbine power output, 97.8 meters. And now we have to calculate how much power we need on the reverse and the charging, right? The same story, but what happens, the friction changes its sides from one side to another side, and you can calculate that's how much power horsepower would be. the pump power, the actual turbine is the efficiency of that turbine times what the ideal turbine would be. So you get 83 meter height of the turbine. For the pump, it's the other way around. You have to divide the power needed by pump by the efficiency. So you have to put in 126 meter height and we finish the pump power. And the ratio of those two guys would be efficiency of your storage system. Again, these are simple academic solution, okay? Usually it's a lot more involved than it's just simple a pipe to go straight up. And so, again, the whole idea is in this course, you're going to review these different systems. Most of you, I don't know how many of you guys knew that 95% of energy storage is hydro. As soon as you talk about energy storage, people think about batteries, okay? It's not there yet. Okay. Now the question is, how are we going to calculate friction losses? So if I have the energy equation, if I have a pump, that means there's energy state 1. I have pump, that means I increase energy. But the energy state 2, and if I have losses, and if there's a turbine there, right? Which usually either happen pump or turbine, doesn't make sense to have two. So the question is, what is the loss? So you simplify it, the frictional loss is F, where F is friction factor. Friction factor is a function of Reynolds number. Roughness epsilon, if you have a tube, if you touch inside the tube, you can figure out how is it rough or is really smooth. So that epsilon shows the information about roughness of the material, okay? Then of course, it depends on the duct shape. Is it circular, square, rectangle, all of that stuff, okay? This is, of course, if you want to get this as smooth as pipe you want to, it costs more money. So the question is, okay, I get a little bit rough, but it's saved a lot of money. The question is, how long you're going to keep this, and when is the time for buyback? You can break even if you spend a lot more on the construction side. So turbulent laminar flow, as I mentioned, the laminar flow speed is the same. It becomes a steady state, okay? And transition changes it, then the turbulent becomes crazy. Is understood. Osborne Reynolds, 1842, 19, so he died about 100 years ago. Okay. What is that CVIT? CVIT? I don't have any idea. I have to ask my TA that typed that up. So anyway, in the flow in a pipe, if Reynolds number is less than 2300, it's laminar. If it's over that, it's turbulent. You're gonna have a sharp transition. That's not the case usually. Transition is over some Reynolds number. Now head loss, the friction factor. Okay, if you have fluid coming in and through a pipe, right? And it's an angle theta, these are the same, right? You guys familiar with that? I think he's using phi, L sine phi is delta Z, right? Toss of W is shear force of the law, which works against your motion. Remember, motion is from top to coming down, x2 minus x1. This is x2, that's x1, is L. Let's assume you have incompressible, steady, mass flow is the same. That means density times volumetric flow rate at state 1 is the same as state 2. Since it's incompressible, that means densities are constant. That means volumetric flow rate would be the same. Volumetric flow rate is velocity times area. And if the area is the same, then that means speed and velocity are the same between 2 points. So it's a fully developed flow. And if you write the energy balance no pump, no turbine, the energy state 1 would be equal to energy state 2 plus loss of energy due to friction factor. So remember I said no pump, nothing. Fully developed, these are the same. So HF would be just delta Z plus delta P over gamma. If you use the momentum equation, how much you remember fluid mechanics? What's the momentum equation? Is F equal ma, right? You guys remember that, right? But F, there are different Fs. 3 different types of force. One is pressure force, right? It's coming down, pressure is higher up there than down here. This is the gravity force, right? The x direction. This is the shear force. Some of these is equal to ma. A lot of the shape basically would be, you can connect it to change of momentum, right? You remember that? And since the velocity doesn't change, so that means your forces is equal to 0. And so delta P over gamma, delta Z is the shear force. And you can see now HF will be related to shear force. That's how we define it. And we can relate, now we can relate to the F. Oh, here, look at that. Moody chart friction factor. That means there's a chart that you have to put in some numbers and you read F friction factor. Because remember, if you're doing it this way, so if you can somehow you figure out what F is, then we can calculate the frictional loss, right? Now combine A and B, so you can see actually F is 8 tau wall divided by rho v square. Tau wall will be different for laminar. For laminar it's easy, you can find a relation. It would be, if you do this, I think it would be 64 over Reynolds now. Okay, but for turbulent it's not that easy because the velocity profile is different and you have to deal with it. Okay, for example, laminar flow in a pipe. That's my velocity. Hey, it becomes from the previous equation. F becomes 64 over Reynolds number. So HF, which is F over 62, you can substitute this and you can calculate Reynolds number, the friction factor. Turbulent flow, that is a relation for friction factor. You cannot solve for it explicitly. Remember, this is 80 years old now. At least it's better from 1700 to 1939. Can you solve for a friction factor? Can your equation calculator does this? You have to do try and error, right? You guess a number, you put it here, and then you solve your friction factor from left hand side. You compare to what you guessed to what you calculated, and if you're equal, hey, you guessed it right. If not, keep trying, and you figure it out. And then there was this guy, Moody. He said, people don't like to do lots of calculating. Remember, at that time, there was no calculator. There was something called a slider. Have you guys seen a slider? It's an antique now. You have to go to a museum, right? Museum of Science probably has. Slider. And it would be complicated because you have a log term and all that stuff that you have to do. So Moody came and plotted this, and here is your Moody chart. So given D, L, and V or Q, rho, all of that, so how to find F. So you have your calculate Reynolds number, which is V times D over nu, kinematic viscosity. If it's laminar, look at that. That's laminar, 64 over Reynolds number. Because Reynolds number is small, eh? Up to that point is a 2000. If you're higher, then it's also here is a roughness, epsilon over D. So you have to say what kind of material you have. What's the pipe diameter? So you calculate, you go basically figure it out, epsilon over D. You figure out your Reynolds number, you point, you match them, then you go left. You figure out Moody's, the friction factor. Right? You're going to do that for homework? I think you do. Is that clear? How to do this? If you question, just email me or comment. We discuss it in the class. Okay. Example. Air at 20 degrees Celsius and 1 atmosphere pressure flows through a 4 millimeter diameter horizontal drawn tube with average velocity of v equal 50 meters per second. In such condition, the flow would normally be turbulent. However, if precautions are taken to eliminate disturbance to the flow, the entrance to the tube is very small, the air is dust-free, the tube does not vibrate, etc. If it may, it's literally not if, it may be possible it may be possible to maintain laminar flow. Fine. Determine the pressure drop in the 0.1 meter section of the tube. If the flow is laminar, repeat the calculation if the flow is turbulent. Let's see how we do this. Okay, we need to remember, find Reynolds number. And the Reynolds number requires viscosity. So you gotta go find a table to find viscosity. Here is for air, so you may have to use this table. That's from minus 40 degrees to 500 degrees Celsius. Viscosity is small number, okay? So we have state 1 and 2, flow in the pipe. Reynolds number is 14,000. Usually it's turbulent flow. Okay. But say, okay, make it really smooth. It's possible to have a laminar flow. So remember, Reynolds number has to be dimensionless number. If they don't cancel out, you're in trouble. Hopefully it does. Normally the flow is turbulent. Energy state 1 plus energy added through a pump is energy state 2 plus the losses and turbine. So if there's no pump, no turbine, the same Z, the same B, delta P here, if I just would be P1 minus P2, I have to multiply gamma times this head loss, right? That would be the pressure drop. And then it would be gamma is rho G, F, friction loss is F, L over D kinetic energy. So you G's cancel out, rho is here, rho V squared. So the idea is what is F? For laminar flow, F is 64 over Reynolds number, right? And you can calculate delta P. Look at that, all my unit conversion. And it becomes, well, very small, 0.171 kilopascal, not much. What's the atmospheric pressure? How many kilopascal?
1 point.
How many psi? What?
10 to the power 5.
Oh, you're talking about this. Kilopascal? Yeah, it's 101, 325 kilopascal. So you can say 1.01 times to the power of 5. What did you read?
101.3. What is those?
1.01?
325.
325, yeah, I told you. 101, 325. Very small pressure. Atmospheric in the inches, psi? You guys are engineers. You guys should know this stuff. It's 14.696 psi. Psi is pound force per square inches. Okay. Okay. Now you want to calculate friction factor assuming turbulence. Remember, with the Moody's chart, you have to calculate E epsilon over D, and here's the epsilon. Recommended roughness value for commercial duct round tubing. This is epsilon. The unit is height because it's epsilon over D, either in feet or millimeters, depending what you have, the diameter of the pipe. So here's the information that you probably need to use. So the friction, of the turbulent is phi. The function of Reynolds number and epsilon over D. Epsilon would be in the case of 4 millimeters, right? I can multiply by 1,000. You get 0.0015 over phi. So this is epsilon over D, very small number. Did you read it? What we had? What was the number? 0.028. That's the answer. So we get 0.00375, and Reynolds number was 14,000, right? Yeah. So we're going to use this chart. On this one, 0.00. So this is 0.001, 0.002. This is 5. So it was 375 something like that. You got to go to the left. 14,000. This is 10 to the 4. So 1.4 wherever it meets, and then you go to the left. What's going to number again? 0.028. So this is 0.025, 0.3. So it was probably somewhere around here. That's one option. The other option, use the equation. Maybe for you guys it's easier to use the equation, right? You can easily program it in your calculator to do iteration and come up with the correct number, because here you guys have to have good eyes, right? And that sometimes causes problem to find a good eye. So delta P would be, I don't know why I wrote it twice, there would be small amount, how much pressure? Only 1.05. So this is 1.05, it's turbulent. What was it if it's laminar? 0.17. So it's about 20%, less than 20%, 17%, 16%. So if you're pumping, let's say you have a pumping station and you have to pump a lot from 1,000 kilometers, let's say. And then the pump power needed would be a lot if you have turbulent compared to laminar. So if you can make it laminar, it helps you because that friction coefficient here, laminar is only this part. Much smaller than the other parts, right? Maybe. Alternate to Moody charge Colburn, same as Moody charge for turbulent flow. So you have the C on the left hand side, you have the square root of F. On the right hand side, you have the square root of F. And you can, I'm sure you guys can use tiny Harmonic solution. There's another equation called Holland equation, and you find this out to be 0.0287. So the turbulent flow is close by, right? There's another one, Lossless equation for smooth pipe. It's a simple one. You don't have to do try and error. You get a number very close to that one because it's simple relation. Okay, that's only true for smooth pipes because it doesn't have roughness in this equation. Okay, it depends how smooth the pipe is. Okay, so you figured out 4 different ways, right? Moody chart, curve log, they're almost the same. So Moody chart, you have to have good eyes. Usually people do one of these and then read the chart. So, okay, I'm close. You cannot do 4 digits by reading the chart, right? It's impossible. So people do that. Now, there are additional losses called minor or local losses in the pipe system. What we taught was just flow through a pipe. Now, there are minor ones. What are they? Pipe entrance or exit. Whenever the fluid comes through the pipe, there is some energy losses. When it leaves also the system, there is an, let's say you have a reservoir, fluid coming through a pipe in, and once it leaves the reservoir, there will be sudden expansion or contraction. Like a step function. Those are losses. Bends, elbows, teeth, and other fittings. Valves, open or partially closed. Gradual expansion or contraction. These are all, there are losses if your fluid goes through these devices. Now, loss coefficient, you can call it K, would be H loss of minor over V. So basically, loss would be K times this. So you need to find K, right? Because this is delta P over 1/2 rho v squared. That's not important. Total loss, then it would be friction loss through a pipe, plus some of the minor losses. So total loss, we can factor out a v squared over 2g. This is the FL over D. This is the K, because you could have many of these, some of the Ks. All right, now how do you find K's now? Resistance coefficient K value for open valve, elbows, and T's. Right. So we have valves, elbows, and T's, flange or screw. These are all plumbing. Different types of plumbing, and you can get different K's. These are K's. Minor loss for K's. Here's another one. What are they? Reynolds number, this is K for 90 elbow. Okay. We have different types of material, plastic, metal elbow, number 1, number 2. Here is for partially open valve. What can the valve be? A gate valve, this valve, glow valve, right? Fractional opening. If this is 1, that means a wide open. Still have on global, we have 2 reactions. The other ones. Okay, so if you want to do this complete analysis, you have to know your K values. What do we have here? It's thinking right for 90-degree bend. So it depends on your roughness of your pipe. Okay. This roughness gets smaller, therefore K gets smaller. What do we have here? Entrance and exit loss. Coefficient A, the entrance, inlet, rounded, and I don't know what that means, the entrance. Rounded and filled inlets. So you can see that's very small. Here, this is the main thing. What kind of L over D. So L, if L is 0, you have sharp edge. With a round entrance or exit, that would be different. What do you have in the sudden expansion, right? Here, you come in, so you have turbulence here, circulation, and that is a friction loss, you lose energy. And you have contraction, so here is extraction, and these are from a book. That's the equation 6 or something of the, I think it's Frank White, fluid mechanics book. Here's another one. It's a gradual, low loss in the gradual conical expansion region. That's calculated by Gibson's suggestion. Okay, so here it is V1, the angle V2. You can figure it out to the cone angle 2 theta, right? Then ratio of diameter, the y-axis of point K. Should we do an example? Okay. In the figure, there are 125 feet of 2-inch pipe, 75 feet of 6-inch pipe, and 150 feet of 3-inch pipe, all cast iron. There are 3 90 degrees elbows, and an open globe valve. Where are they? Okay. All flange. If the exit elevation is 0, what horsepower is extracted by turbine, and the flow rate is given. Okay. For water at 20 degrees Celsius, whenever you don't know the temperature, assume it's 20 degrees Celsius. Do you guys have a feeling with 20 degrees Celsius? Do you have an idea? Do you convert it to Fahrenheit? What is 20 Celsius? 65? Not really. Remember, we're scientists here, right? 68. Every degree Celsius is 1.8 degree Fahrenheit. So if you said 10 degrees Celsius, it's 18, so it takes you from 32 to 50. And the second 10 is another 18, takes you from 50 to 68. Maybe that gives you a better feeling, right? Water is 68 degrees Fahrenheit. If you go live in Europe, you gotta get used to it, degrees Celsius, okay? Because you walk around and if there are banks everywhere that show the temperature of the air, they write degrees Celsius. You can convert it to Fahrenheit right easy. Okay, density is 1.9 for a slug per cubic feet. That's viscosity. For cast iron, you can look up and you say roughness. And 2 inches, 6 inches, 3 inches respectively. You calculate L over D, epsilon over D, right? The flow rate is known, so each velocity, Reynolds number, and F can be calculated. So the velocity is flow rate, 0.116, divided by the area at different part. Based on that, they can calculate Reynolds number, 113, and they have to go find friction factor. That's the Moody chart, or those equations. So for B, the same thing. And we have B, friction B, friction C. Finally, the minor loss coefficient may be tabulated. Sharp 2 inches entrance, K is 0.5. 3 2-inch 90 degree elbow, K is 3 times that. 2-inch sudden expansion. All those charts that we went through it quickly, you need them. 3-inch open globe, K is almost 6.3. So the turbine head equals the elevation difference. Remember, the velocities would be 0. Minor losses and exit velocity head, except the exit. So you have delta Z minus friction minus minor minus the velocity at the exit. So here you substitute all the numbers. You got the turbine head is 72.8 feet. The resulting turbine power is density, specific weight, Q times HT, small turbine, 1.32 horsepower. We done? Hey, we're done. So, we went really fast on this one. Huh? If we go with this speed, we're done in 3 weeks. Yeah, but this is something you already knew. It's mainly potential energy difference, which is Z. And then the only thing that some of you may have some issue is that the calculating of frictional losses. But everybody said you guys have seen this before. Everybody seen it before? The chemistry major? Never saw it before? You're learning something new, that's a good idea then. These guys say, I didn't know this stuff. Right. So you need to be patient, because there would be homework which is already uploaded and requires this kind of stuff. If you have any problem, either email me or Sai. You guys know who Sai is, right? I've been trying to, when I send emails to you guys about the footprint size, copied and that email. So contact him or me. I think he's younger, he's smarter, and he will answer your question much faster than I can answer your question. Remember, you guys, you know about civilization, right? Civilization got better every time from when you start 7,000 years ago. There's always issues with who was first, Chinese were first or Egyptians first, who cares? But look at the civilization, it gets better and better. That means, on the average, new generation is smarter than the older generation. Period. Okay? Because things are getting better. Right? There might be, like these guys we talk about, Reynolds, this guy, once in a while you find people that were really smart and their name stays in the history for many years. Okay, like Newton guy. 300 years ago, he said, hey, FGLMA. Did anybody prove that to you guys? Have you seen the proof of FGLMA? No. Based on observation. And nobody has said, no, based on my experiment, this doesn't work. Okay? Lots of scientists make an observation, they make a statement. Some of them are right, some of them are wrong. Okay? For example, a few years ago, there was a scientist in Utah, he said we have cold fusion. You know, fusion is you fuse some atoms together and you make a new atom. The mass is less than sum of these two, so you lose some energy mass and convert the energy equal mc squared. But in order to fuse atoms together, you need very high temperature, right? 10,000 degree Kelvin. And of course, when you do that, it diffuses and you get energy, but so far, the energy you got out is less than energy you put in. So these scientists came in, hey, I got room temperature fusion. Okay, you might say, wow, look at that. Solved all the whole world's problem with energy. We wouldn't be here if the fusion works everywhere, right? But people did the experiments and no, this is wrong. He's seeing something else. So by default, you're smarter than me, so you can, if I know this stuff, you guys can learn it right away, quickly, much faster. Right? You agree with me on that? The reason you may know I know more, because I've been at it for the last 40 years, okay? But if it comes to your gadget, electronic gadget, it's clear you know a lot more than me. You can do it faster. Anyway, we're here, we finished number 1, we got to go to 19 items, right? We're done with number 1 and see what we do tomorrow. Okay? Have a nice day, see you tomorrow, talk to you later. Have a nice day.